Yeah, so let's get started. Thanks for having me. Today I'm here to talk about gRPC load balancing and the case when Kubernetes load balancing is seemingly not enough. Yes, I'm Dominik. I work as a senior software engineer, and I also happen to be an ambassador for this thing called Linkerd. You can reach out to me on the Linkerd like at Dominik, and my GitHub handle and my GitHub page should have the other ways you can reach out to me, and of course you can talk to me after my session. And let's get started. So first of all, let's take a small trip down memory lane and look at how communication looked like in distributed systems a while ago and how it looks like now. So no surprise, in the past we had monolithic services and monolithic applications, so the application in itself was protected by the process boundary. We didn't really have to think about how they should talk to each other because it ran as a single process. Now we have microservices, of course, and most of our applications are running as separate services, and of course we had to find a way for these services to communicate. And one of these ways was, of course, REST. I think that's the one that most people are already familiar with. It's a resource-oriented way of communication. I also have an example coming up that explains what resource-oriented and action-oriented is. And yeah, we have RPC. It stands for Remote Procedure Call. It's an action-oriented way. It has multiple flavors: JSON RPC, HTTP RPC, and gRPC, the topic of the talk. And of course, we have GraphQL and WebSockets. Those are also pretty widely used today. So here's an example on what action-oriented and resource-oriented is. So on the left-hand side, we have REST. So let's imagine that we have a backend service with a database. It stores cars. And how do you create a car? I guess it's pretty self-explanatory. You send the post request to the/cars endpoint, and you specify the specifics of the cars in the payload. So the make, model, year, color, price, and yeah, all the other fancy things. And then you have a car in your database. For RPC, I have a slightly different example. So let's imagine that we have a service that verifies transactions. And in RPC, actually JSON RPC in the example, you will specify the method that you would like to invoke. So it's verified transaction in this case. And in the param section, you would verify the transaction ID of the transaction that you would like to verify. And you will get back like the status of the transaction, if it's valid or not. A slightly better example is maybe it would be a calculator application. So if you want to model a calculator application, it wouldn't be that straightforward in REST. So what would your endpoints be? Which HTTP verbs would you use? So would you use post to add two numbers or multiply two numbers? Would you use get or put? And if you think about it, modeling it in RPC is a lot easier. So in the method section, you would specify the mathematical operation, and the param section, the numbers that you would like to pour from this action on. And so the topic of this talk is gRPC, and what makes gRPC stand out. gRPC uses protobufs or protocol buffers. It's a serialization framework, and that's what gRPC uses. So it doesn't use a human-readable format like JSON RPC. It uses protobuf, which is binary, so it improves performance by a lot, and that's why it's so widely used between microservices even today. And I forgot to ask, who uses gRPC in production? All right. So it's defined using these protofiles. It describes the data structure and the services themselves. And what's great about it is you can use these protofiles to simplify development, because you have like a descriptor file of your service, and you can generate lots of boiler code from this one. It's language and platform neutral, so you can use it in C, C++, Go, Rust, Java, and yeah, all the other fancy things. Right. And yeah, so this is what a protofile looks like. So it goes back to the previous transaction verifier example. So we have a service called transaction verifier. It has one method, verify transaction. It takes a verified transaction request as an input and returns a verified transaction response. In the request, you specify the transaction ID, as I said so, and in the response you get whether it's the status of it, which is an enum, so it's unknown, confirmed, pending, or failed, and then you take this protofile and generate your boilerplate code from this one. And I have an example application, the emoji Voto application. It's available on GitHub. It consists of 3 services and a traffic generator. The traffic generator uses REST to communicate with the web application and generate traffic, and the web emoji and voting applications use gRPC to communicate. And yeah, let's explore our application. It's actually not that one, this tab, yeah. So this is what the application looks like. You can vote for your favorite emoji. Let's pick this ghosts. And clicking on this one invokes the voting service. And if we check the leaderboard, this one invokes the emoji service. And here you can see all the traffic already generated by the traffic generator. And let's take a look at our applications and our pods. It's in the emoji vote namespace, and we have 5 instances of the voting application. There's a reason for this. 1 instance of the vote bot, 1 instance of emoji, and 1 instance of the web application. These are, of course, deployed as deployments. And I also have Prometheus running, and I also have a persist dashboard for the resource usage of the applications. And this is just for the voting application, which uses gRPC. And as you can see, there's something wrong with it, because it looks like one of the pods is doing a lot more than all the others, basically like double full of the others. And yeah, let's check the logs of our applications first to see what's wrong. So auto completion is helping me out a lot here. So let's check the first pod. It was v6. And let's follow the logs, and yeah, you can see that traffic is generated. All right, and let's check the second pod, which starts with a 9. And seemingly there's no traffic on the pod. Let's check the next one. Sorry for switching between dark theme and light theme. I know it's not pleasant. Let's check the third one. This one was also not getting any traffic, and the fifth one is also not getting any traffic. So please trust me that the application is working correctly. It's nothing wrong with the application. Let's go back to the slides. So I created a screenshot just in case if my demo didn't work. And yeah, so let's take a look at how Kubernetes load balances requests. So if you have a deployment, for example, and there's a service in front of it, and you want to communicate with the service itself and the deployments, you use DNS name, of course, and the DNS name gets resolved to an IP address, and the service picks one of the pods that's going to receive the traffic. And you might be wondering that, okay, I guess it load balances the requests correctly, it uses round robin, and yeah, all the pods are happy. And yeah, that's not the case, because Kubernetes services don't exist. They never did. They are just virtual IP addresses, if you're talking about cluster IP services, of course. And these IPs are allocated by the control plane, and they are stored in etcd. And how it works is that the kube proxy on every node is subscribed to endpoint slices and services. And whenever there's a change in either of them, either of your services or endpoint slices, it's going to update the internal state of your node using IP tables. So it updates the IP tables rules and how the routing works. So let's take a look at it in action. Let's use this one, and let's SSH into our Minikube cluster, or our node. And we can actually check the IP tables rules right here. These are pre-routing rules. Let's add line numbers. So yeah, this is called a chain, and the number ones are, of course, the rules that it uses, and we can dig deeper into the kube services rules. So it's I should just use this one and add -n, and we want to inspect the kube services. Yeah, hopefully it's readable. So as you can see, maybe even better from the annotations, there's one for each service that's running on our node, and we can try to find the voting one, which is this one. And if you check the IP address 1096.209.84, and if I get the services, it's the same IP address as the voting service. And we can check the rules which belong to this itself. So and these are our pods backing the service. So we have 5 pods, of course, and you can see the IP addresses of the pods right here. And what happens is that if the node sees this IP address, the target IP address as this one, then it's going to substitute it into one of these ones. And you can also see the load balancing probability right here. And so 20% chance that it gets routed to this one, 25 that it goes to here, 33 that it goes here, and you can already see that the numbers are not adding up because it should be 100%. But unfortunately, that's not how IP tables routing works, because these rules are processed sequentially. So let's imagine that you have a request incoming and it reaches the first pod. Then there will be a 33% chance that it gets routed to the pod, and another 67% that it goes to the next rule. And after that, you have 2 pods, of course, so 50% chance that it goes to pod number 2, 50% chance that it goes to the next rule, and at the next one, it's of course 100%. So yeah, you can even see it in this example. So 20, 25, 33, 50, and 100%. Yeah, so then why is my load balancer not load balancing in the case of our application? So gRPC is built on top of HTTP2, and gRPC makes use, or even HTTP2, sorry, makes use of a single long-lived connections, and your requests are going to be multiplexed through this one. So you can achieve like true parallel processing with HTTP2, and you can have like multiple request response flows happening at the same time. There's no head of line blocking, and yeah, you have a one-to-many connection between the connections and requests. So connection level load balancing. So Kubernetes does connection level load balancing, and it's good enough for HTTP1, but it's not good for HTTP2, because the pre-routing rule that I talked about previously gets invoked once when the connection is established, the gRPC connection, and it's going to keep using this one connection as you saw in the demo. So that's why only one of our pods is receiving traffic. And you might be wondering that, okay, but HTTP1 also has long-lived connections, and isn't it the same case with HTTP1? And yes, but actually no. Because HTTP1 processes requests sequentially, and it has head-of-line blocking. So if you send 10 requests, and the first one takes a long time to process, then it's going to block the other 9. And HTTP2 can process these in parallel. And HTTP1 was built to be good at connection recycling, and even these long-lived connections expire after a while. And that's the reason why connection level load balancing is good enough for HTTP1, but not for HTTP2 and not for gRPC. Yeah, so let's take a look at request level load balancing. So to achieve request level load balancing, we need to shift our load balancing logic to layer 5 and layer 7 instead of layer 3 and layer 4. And we would need to maintain a connection to each of the pods from our source. And we would need to load balance the requests among these connections ourselves on the client side. So in your application, you would need to watch the Kubernetes API, look for changes in services and endpoint slices. If there's a change, you need to fetch the endpoints of the pods, create a connection, or even delete a connection if one of the pods is destroyed, and yeah, add a connection if a new one is created. And so whenever there's a change, you would need to update it. And of course, you would have to do it for each of your applications. If your applications are written in different languages, then you would need to do it in each of them. Or of course, you could create a proxy yourself and maintain it. Or you could make use of a service mesh. And this is where Linkerd comes in. It's ultra-fast security-first service mesh for Kubernetes. It was created by a company called Buoyant. It's been in production for a good while. I think it's actually 9+ years now. And it's used by a wide variety of companies. And it's actually the first graduated service mesh. And Buoyant was actually the company that coined the term service mesh. So that's the origin of it. And how does Linkerd solve our issue? So Linkerd uses sidecar container, so it places another container in between or next to each of your pods, and all of the network traffic is going to flow through this proxy, and the proxy is going to be the one that's going to maintain the connection, maintain this connection, pool and load balance requests. So Linkerd works with any language, any gRPC client, any deployment model. You just deploy it besides your application pod or application container, and it just works, I swear. And it uses AVMA to load balance requests. It's exponentially weighted moving average, and in short, what it does, it's going to shift traffic away from your slow pods, and so if there's a slowdown in one of your pods, then it's going to shift traffic onto the other ones, and if it speeds up again, then of course it's going to keep moving traffic back to it. It uses a Rust-based proxy, so the resource usage is pretty negligible compared to all the other service meshes, even ambient mesh, which we found out from our recent benchmarks. And it has MTLS out of the box, so if someone is sniffing the network package, then they won't be able to read it. Tying back to the previous presentation, so it's mutual TLS, and I have another demo coming up, and this one is the last one. So we are going to fix our application by adding the get the deployments, not this way, but this way. And let's do the voting first. It uses this inject command, and we are going to pipe the YAML into Linkerd inject, which is going to output the YAML which has the annotation to add the sidecar container, and we're going to apply the YAML file. And let's do it also for the web part, because you have to mesh both sides. And now we just wait, get the pods, and we are going to modify our Perseus dashboard a little, because the old pods are also going to show up. And so it's voting in dash, and this is the new deployment. Let's copy it. Right tab. And let's also do it for the memory usage. It doesn't affect it, but that much. Right here. And why we get data? It's going to work, of course. And so Beyond does this Service Mesh Academy. It's a monthly hands-on training from the creators of the Service Mesh. We cover different topics like certificate rotation and all the new features like multi-cluster, Linkerd multi-cluster. And if you want to check it out, feel free to do so. And there's also this Service Mesh certification course. It's like Linkerd 101. It's a self-paced online course. You do it in a demo environment similar to the Kubernetes certification exams. And there's also you get a LinkedIn badge. That's the most important thing, I guess. And there's also a Linkerd in production course coming soon. And let's take a look at our Perseus dashboard, whether it's caught up or not. And if it didn't, then we can of course check the application logs to make this slightly faster. So get the pods and kubectl and voting, and let's check the first one. Right. It's the wrong pod, sorry. Alright, so the first one is receiving traffic, the next one was GBK. It's also receiving traffic, so we are already better than the first case without the service mesh. And let's check the third one. That one is also receiving traffic, so we fixed our cluster, and Yeah, and you can see the CPU usage that basically all of the pods are receiving almost the same amount of traffic. It could be that one of the pods is slower on my cluster, and that's why the traffic is shifted away from it. But yeah, everything was just as expected. And again, thank you very much for having me, and thanks. And yeah, feel free to applause.